Assalamualaikum and very good morning to my panel, Dr. Abdul Hakim bin Abdullah and Dr. Anizah binti Kalam. My name is Mohamad Aisamuddin bin Mohamad Shahrum. Today I will present about my final year project which is development of recycled PVC fly ash composite. My project is under supervision of Dr. Fredawati binti Rashidi Wong and Dr. Yang Sung Kong. Firstly, I will share about my project summary. The polyvinyl chloride waste is estimated to increase from 44.3 million tons to 59.72 million tons over 2025. The statistic of PVC waste that goes to landfill is 82% and 50% to incineration, while for recycling is only 3%. The toxic gas released from incineration may threaten human health, which causing asthma, brain damage, and pulmonary cancer due to inhalation of poisonous gas. The toxic additives such as mercury, chlorine, and dioxin from the PVC waste in the landfill may leach and migrate into the river or ocean, causing the deaths of marine life. Besides plastic waste, fly ash also one of the waste problems in Malaysia that produced during combustion in power plant. Fly ash may cause land pollution and water pollution that lead to human health problems. This study is an initiative to recycle the PVC and fly ash into new engineering construction material such as pavement in order to reduce the waste end up in landfill and incineration. In my project, I list two objectives. First, to determine the base ratio of PVC fly ash with the optimum mechanical properties using tensile test. Second, to determine the thermal properties of PVC resin and recycled PVC using differential scanning calorimetry and thermogravimetric analysis. In this part, I will share the methodology of my project. Before I prepare the composite, I run two thermal analysis for PVC resin and recycled PVC, which are differential scanning calorimetry to detect the melting point of the polymer, and thermogravimetric analysis to observe the thermal degradation of polymer. After finish the thermal analysis, I go through to primary process of recycled PVC. There are three steps under primary process. First step is material collection. In this step, I collect the recycled PVC at recycling center in Klang. Next, I clean the recycled PVC using detergent to remove contaminants at the PVC. Lastly, I shred the recycled PVC using shredding machine into small particle, and the size of particle is below 4 mm. After that, I go through preparation of recycled PVC and fly ash composite process. The first step in the process is mixing. In this step, I prepare 5 different parameters which are 100% recycled PVC, 0, 5, 15 and 20% weight percentage of fly ash content in composite. Next, I continue with extrusion process. In this step, I use hot twin screw extruder. The extrusion process was run in temperature range 175 Celsius and the speed of extrusion is set 65 rpm. The composite was extruded in solid wire sheet. Next, it continued with compression process. In this process, I use hot compression with temperature range 175 Celsius with pressure 10 megapascal for 7 minutes. The compression process produced a PVC fly ash plate composite with 3 mm thickness. Lastly, I cut the plate into dumbbell-shaped specimen using vertical saw, follow the dimension in ASTM D638 Type 1. After finished preparation process, the composite will go through testing process, which is tensile test, and continued with numerical analysis. In this part, I will share more detail about the testing and analysis in my project. Differential scanning calorimetry is used to determine the melting point of resin PVC and recycled PVC. Sample about 7 mg was weighed, transferred and sealed in the aluminum pan and heat under temperature range 10 to 350 Celsius. The heating rate was set at 10 Celsius per minute and the gas flow rate 20 ml per minute. The significance of this analysis is used to detect the melting point of the polymer and can be used to set the temperature range in the extrusion and hot compression process. Therefore, we can avoid the polymer from degrade faster when exposed to hot process. Next is about thermogravimetric analysis. TGA used to determine the thermal degradation of resin PVC and recycled PVC. Sample about 7 mg was weighed, transferred, and sealed in aluminum pan and heat under temperature range 10 to 500 Celsius at heating rate 10 Celsius per minute under gas flow rate 20 ml per minute. Lastly, I will share about the tensile test parameter. The tensile test will run use Universal Testing Machine, referred to ASTM, D638 Type 1 using dumbbell-shaped specimen. The crosshead speed was set at 5 mm per minute at room temperature. Basically, the tensile test used to determine Young modulus, yield strength, ultimate tensile strength, and elongation and break. The mechanical properties from the tensile test is used as reference to produce pavement that can withstand with maximum force. In this part, I will share result and discussion from the tensile test. The first mechanical properties is Young's modulus. From the graph, we can observe that the maximum value occurred at 100% recycled PVC content, which is 29.19 megapascal. At 5 weight percentage of fly ash, it results highest value, which is 22.97 megapascal compared to the other composite that have fly ash content. In general, the higher Young's modulus is solved when deflation is not important, while lower Young's modulus is required to produce flexibility product. Therefore, it observed that the minimum value of Young's modulus is at 10 and 20 weight percentage of fly ash. It is an ideal composition as the project is to produce pavement that has high flexibility. Next, I will share about the yield strength of the composite. In general, by adding the fly ash in the composite, the value of yield strength increased slightly. The maximum yield strength occurred at 10 weight percentage of fly ash, which is 0.87 megapascal. Yield strength is a stress at which the material exhibits permanent deformation and cannot return to original shape. The increasing of yield strength because of the fly ash tend to reduce the void content in the matrix. However, the value of yield strength decreases linearly with the addition of fly ash content after 10 weight percentage due to agglomeration. The agglomeration happens when the fly ash forming lumps in the composite. Hence, it causes non-homogeneous PVC fly ash composite. The study of yield strength is important to detect the highest force of the composite that can withstand before it deflects. Next, I will share the tensile strength of the composite. From the graph, we can observe that the maximum value occurred at 100% recycled PVC content, which is 1.96 megapascal. The tensile strength in the composite that have fly ash also show improvement at 10 weight percentage of fly ash, which is 1.7 megapascal. From the result, it observed that incorporation of fly ash improved the tensile strength at 10 weight percentage of fly ash, although it does not exhibit 1.96 megapascal. This is because a lower fly ash particle provide high surface area to polymer interact with the filler. Hence, it improved the addition between filler and matrix. However, the value of the tensile strength decreased linearly with the addition of fly ash content after 10 weight percentage due to agglomeration. The agglomeration happens when the fly ash forming lumps in the composite and cause non-homogeneous PVC fly ash composite. The study of the tensile strength is important to detect the highest force of the composite can withstand before it broken. Therefore, the value can use as reference to produce pavement that comparable with the commercialized product. Next, I will share the result of elongation and break in my study. The incorporation of fly ash within the composite show improvement until 15 weight percentage of fly ash. The maximum value occurred at 15 weight percentage of fly ash, which is 37.39%. From the result, it's significant that higher fly ash content can make the composite elongate more. In general, the recycled PVC employed in the current study was recovered from flexible wire and cable contained with the plasticizer. Thus, the plasticizer can interact with the silica component in fly ash, which improve the dipole-dipole interaction between filler and matrix. As a result, the elongation at break increased because of the synergistic impact produced by the plasticizer and the fly ash in the recycled PVC. However, at 20% weight percentage, the elongation at break in the composite reduced due to the larger volume of fly ash filler compared to the PVC matrix, resulting in agglomeration. Next, I will share the result from the DSC analysis. The DSC curve from figure recent PVC shows the melting range from 167 to 183 Celsius with the endothermic peak at 170 Celsius. The DSC curve from recycled PVC shows the melting range from 173 to 180 Celsius with the endothermic peak at 178 Celsius. From the result, it is observed that the recycled PVC has the higher melting point compared to resin PVC. The additive in recycled PVC tends to hold the polymer chain in solid polymer. Therefore, more temperature required to break the polymer chain and melt the polymer. The melting point that get in this analysis was used to set the temperature in extrusion and compression process. Next, I will share the result from thermogravimetric analysis. The resin PVC curve shows three recognized steps of degradation. First degradation is elimination of chlorine at temperature below 300 Celsius. Second degradation is about cracking of hydrocarbon backbone at temperature range at 400 to 600 Celsius. Lastly is degradation of residue. From the result PVC curve, it only shows two steps of degradation. The weight loss in the resin PVC is 64%, while the recycled PVC is 44% when the temperature is below 600 Celsius. In this case, recycled PVC degrades slower than pure PVC due to major additives in the recycled PVC polymer such as stabilizer and plasticizer that help to improve the thermal properties of the polymer. In this part, I will share the conclusion of my project. The composite of recycled PVC from waste electrical wire and industrial of fly ash was successfully prepared using an extrusion technique followed by the compression molding. The Young's modular decreased with increasing of fly ash content, which is attributed to higher flexibility of composite. Both yield strength and tensile strength increased by incorporating fly ash in the composite until 10 weight percentage of fly ash, indicating good interfacial bonding between the filler and matrix. The maximum elongation at break improved until 15 weight percentage of fly ash. The thermal properties of recycled PVC is higher compared to the PVC resin due to the additive present in the recycled PVC. From the mechanical properties, it can be concluded that 10 weight percentage of fly ash is an optimum ratio to produce pavement from PVC and fly ash waste that can withstand high force and at the same time has high flexibility. The addition of coupling agent and stabilizer can be introduced in the next project to improve the mechanical properties of PVC and fly ash composite. That's all from me. Thank you.